let's review what we know about alkynes so far. We'll start by how you make them. If you have a dibromo species, either with the bromines on the same carbon, which would be geminal, or on different carbons, vicinal, but right next to each other, then you can use two equivalents of a strong base. Here I have drawn LDA, but heating it up with a ton of hydroxide will work as well. Dual E2 eliminations will give you the alkyne. We have already encountered how you can use an alkyne in synthesis as one of the very few ways of making a carbon-carbon bond, and we can do a pair of SN2 type reactions. So deprotonating with sodium hydride, which has a pKa of 35, and the alkyne has a pKa of 25. Deprotonating makes the anion at this position. Treatment with methyl iodide in some SN2 capable solvent then leads to the propyne. So we've added methyl to the double bond. We could do it again. I could use a different base with a pKa that's strong enough. LDA is another option as well, of course. And I can make the anion at this position, which will then react eventually in an SN2-like fashion with an alkyl bromide. And that could then lead to material that now has been elaborated. So you make alkynes so that you can use them to make carbon-carbon bonds, essentially. But I also mentioned previously that this is only useful if you could then carry it forward in some sense. And so if you wanted to elaborate this into double bonds that we can now use in addition reactions, then lithium in ammonia or sodium in ammonia, either case you're using the metal in a dissolving metal reduction, and you will make the trans material. It will stop halfway at the alkene position. Likewise, Lindlar's and hydrogen is how you make the cis alkene, and you can again stop halfway. Then of course, if you wanted to continue on, or if you wanted to get there directly in a single step, hydrogen gas and palladium on carbon will take you to the pentane. And again, you could go via the same exact hydrogen gas palladium on carbon from the alkyne, and you can arrive at the alkane product. So this is what you already knew before, but we now have information about how double bonds react in the presence of things like HCl and Br2. So let's back up to here and consider what happens when we react with other material. So let's say we wanted to react this internal alkyne with HBr. Then based on the mechanisms that I've showed you before, what you would assume is that the double bond will need to do an attack on the hydrogen, and then the bromide is going to find a way to insert itself back into the two cations that result. The problem here, of course, and I hope you recognize, that you will end up making two possible cations, and there's really not going to be a whole lot of difference between these two. So it's not clear which cation you'd prefer. They're both, in a sense, secondary. They're vinylic because you have a double bond there, which means that they're relatively high energy, but there's not going to be a whole lot of preference there. And so the result of this particular reaction should be to make both products. Since there's no preference in terms of cation stability, at least that's visible at the outset, then you might anticipate making both products. The HBr addition, if you have a single equivalent, will add once. And the reason for that is, though an alkyne is slower to react than a normal alkene in the first place, if I had to choose between this reacting or a normal double bond, the double bond would react first. Once your product has formed, you have a electron withdrawing group, something that's pulling electron density away from the double bond, and these double bonds will be slower to react than the original material. So if you use one equivalent of HBr, you're going to make one or the other of these. However, if you then use a second equivalent of HBr, what's going to happen is you end up making the geminal species. This material will be converted into the dibromo species, whereas the other material will be converted into the other dibromo species. And you can figure that out by drawing out the mechanism and trying to decide which cation will end up more stable, and that's why you end up with the dibromo, the geminal dibromo species. So anyway, if you add a single equivalent of HBr to a triple bond, then you make the double bond species. If you then add more HBr, you can continue on and make the geminal dibromo species. Obviously, of somewhat more interest would be if this material that was terminal reacted in a similar manner. If you do the initial attack, then the first intermediate that you need to contemplate is going to be the one where you have the cation at the secondary position as opposed to the primary, and there really is a preference, and so your bromide, which is floating around, will then go ahead and add purely at the secondary position. You'll get none of the primary product. So as long as the alkyne is terminal, then you will get selectivity for the Markovnikov product as expected. It's just in this particular case, you can't decide which of the two cations is more stable. So you can add HBr A single equivalent of HBr will add 1, another equivalent of HBr will add a second round, and you will end up with the dibromo species, and specifically the geminal dibromo. And again, if you want to figure out why that is, draw out the mechanism for it. You'll see it. Of course, we can do things like add bromides and chlorides across the triple bond as well. The mechanism will be identical to the chloronium or bromonium species that we've talked about before. The result is that you end up making dichloro species. In this case, it would be the vicinal dichloride, by which I mean you would have 2 chlorines on nearby carbons. And likewise, in this case, what you'll end up making is the vicinal dichloro species as well. And if you were to add in a second equivalent of Cl2, then again, you could react further and make the tetrachloride species. So adding halogens across the triple bond works as you'd expect. Where things get different and a little weird is if you try to add water across these. And so we will now say that you can add water in a Markovnikov fashion in the presence of mercury. Mercury sulfate in the presence of, say, sulfuric acid and water will then lead to an interesting product. The outcome here, when all is said and done, is going to be probably unexpected. You will make the ketone. And for that, we have a long and complicated mechanism, and we will go through an enol type product. So the other thing that I want to point out is if you start with the exact same material and you would like the anti-Markovnikov addition, then you can add borane. And of course, borane itself will work, but 9-BBN will be more selective. So you might see other borane reagents. And as I've shown you before, one way of thinking about the 9-BBN is to draw out this shorthand. So you use some relatively large borane reagent to get some selectivity, and then the boron will end up adding at the anti-Markovnikov sense. So upon oxidation of the borane, you end up making the anti-Markovnikov product, which is to say the aldehyde. Again, you're going to go through a keto-enol tautomerization process along the way, and I'll draw out the mechanisms for both of these in just a moment. But the message is that you can do a Markovnikov addition of water across a triple bond by using mercury, and you will isolate the ketone at the other end. You can do an anti-Markovnikov addition of water with a borane, and if you want it to be relatively selective, you use a relatively large borane. 9-BBN is what I have drawn there. One others that will show up is what Professor Miller refers to as dicyamyl borane, which essentially amounts to having this strange, relatively large reagent. This relatively bulky carbon group is the cyamyl that's referred to there. What exactly is creating the bulk doesn't necessarily matter. What matters is that you have a BH bond and some large group that gives you the selectivity. Using a relatively selective borane, you end up with the aldehyde after oxidation of the species. One other thing I want to point out here is that when you're doing the mercury, you don't need the sodium borohydride reduction. It will just fall off on its own in the presence of acid, and so that's interesting, and we'll get into that when we consider the mechanism.